All right, an intro to probability. Now, the idea of probability isn't what happens in one trial or 5 trials or even 100 trials. The idea of probability is what happens over the long run through many, many, many trials. Probability is the percentage of times something favorable happens over the long run. So we call it long run relative frequency. Remember, relative means percentage and frequency means count. So remember, for the basic idea of probability, and we would write it like this: the probability of an event A occurring would be the favorable outcomes versus the total outcomes. And that's basic probability that you guys have probably dealt with before. So it does work out to be a percentage, but you have to understand that we've done simulations that try to find probability for us. The idea is that, we might all expect something to happen on one given trial, but we understand that over the course of many, 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 many trials is when the true probability of an event occurs. So that's why we refer to probability as the long run relative frequency. It's what's going to happen in the long run, not necessarily right now. So we have this idea of random phenomena. Random phenomena, think of as a chance experiment. Okay, this is a chance experiment. And this is basically saying that, anything where we don't know the outcome, so any type of situation where 2 or more things could happen is a random phenomenon. Okay, so we like to think of the sample space as simply a list of all the things that can happen. List of all outcomes. So if we think of something quite simple like flipping a coin, my sample space would be written like this, and we use these little squigglies to represent the sample space, would be heads and tails. Boom, that's real simple. Those are my two outcomes. Those are the only 2 things that can happen when I flip a coin. But there's many, many other chance experiments or random phenomena out there where there are many more things that can happen. Okay, think about driving your car towards a red light. When you're driving your car towards a red light, 3 things could happen. You could hit the red light. It could be a green light, or it could even be a yellow light. And those are the 3 outcomes in that chance experiment. When you're talking about pulling a card from a deck, there are many, many, many things that can happen when you pull a card from the deck, because we know that there are 52 cards. So if we're talking about pulling 1 card, well, then the sample space would be the 52 total outcomes of all the different cards. Sorry, this is going to keep popping up. So we got to really think about all of those different outcomes. That's our sample space. Even throwing a dart at a balloon, we've seen that examples before. You're either going to hit the balloon and win a prize, or you're not going to. So those are your outcomes. Also, rolling a die is a favorable one. This happens a lot, right? So when we roll 1 die, we get a 1, a 2, a 3, a 4, a 5, or a 6 can happen. Okay. When we roll 2 die, we're going to look at that a little bit later. Then there's many, many more options can happen. So the idea, hopefully, here is quite simple, trying to figure out these chance experiments here. Now, what happens is that a random phenomenon has trials. So we flip the coin. That's 1 trial, and the outcomes are heads or tails. Okay. Now, the idea of probability is what happens in the long run. So in 1 trial, we might get ahead. That doesn't mean we stop and we claim that the chance of getting ahead is 100%. Obviously, we'll do it again, right? So maybe we run 10 trials, okay? And while we're running 10 trials, we get head, 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 we get it in a tail, and then we get a head, then we get a head, then we get a tail, then we get a head. That's 1, 2, 3, 4, 5, 6, 7, 8. Then we get a head, and then we get a tail. So those are our 10 trials. And over the course of these 10 trials, we counted 1 success, 2 success, 3 success, 4, 5, 6, 7. So 7 out of our 10 trials, we were successful in getting ahead. Does that mean that the coin has a 70% chance of getting ahead? Absolutely not. What that tells us is that in the long run, if we did this not even 100 times, because we might not expect 50-50 over 100 times, not even 1,000, we're talking an infinite number of times. Sorry about that. I don't know what's going on there. So many, many, many times, right? That would be the idea of long run relative frequency, which is probability. What's going to happen over the long run? So a phenomenon has these trials, and each trial has outcomes, and the outcomes can be combined to make events. Okay, so that's the basic idea of probability, but I just want you guys to understand that what we've been doing is simulations. It was just running a set amount of trials. That's not going to exactly be the true probability in the long run. So our goal is to kind of investigate finding true probability over the course of the long run. Okay. Now, while we're doing this, there are two important terms I want to introduce now because they're going to be important throughout the entire unit here. And the two terms, the first term is mutually exclusive or disjoint. Mutually exclusive are two events that cannot happen at the same time. For example, when we flip a coin, heads and tails are what we consider mutually exclusive events or disjoint. Those two events of a head or a tail can never happen at the same time. However, when we do something a little bit more involved, like say pulling cards out of a deck of cards, we could have some mutually exclusive events. So think of the idea of getting a red card. Think of that as an event, right? Getting a red card. That is one of our events. And another event is getting a heart. Okay. Well, could those two things happen at the same time? Well, yeah, you better believe they can happen at the same time. If you get a heart, it's going to be red. And if you get a red card, it could be a heart. So those are what we call disjoint events. Well, I'm sorry, these are events that are not disjoint. Okay, I'm showing an example. It's not disjoint. So these two things could happen at the same time. So that's why we say those are not disjoint. Could a card ever be a spade and a red card? Well, no, this can never happen at the same time. These two events are disjoint. There are no cards that are both spades and red. So these two events could not happen at the same time. So those are examples of disjoint events. So remember, mutually exclusive or disjoint are two events that cannot happen at the same time. Now that's going to be really important when we do some later examples. The next idea is independent events. And independent events are the outcome of one event does not influence the outcome of a second event. So again, independent events are when the outcome of one event does not change the outcome of a second event. For the most part, when you roll a die doesn't have a brain. So if you roll a 2 can happen again, and then a 2 can happen again, and then you can have a 2 happen again, and you could potentially roll 5 2s in a row. Now that might be very rare, but it could happen. So the idea of independent events is that the roll of one die does not affect the roll of the next die, and that is certainly true with die. Now, we have to understand that when you're picking cards out of a deck, this could change, right? So if we're going to pick a card out of a deck and not replace it, so say we have 52 cards, right? And we pull out the 2 of hearts. Now, we have gotten our 2 of hearts, and maybe we want to get a flush, which means all the same suit. So I want to get another heart. Well, the problem is, now when I reach back in, the fact that I've already taken out a 2 of hearts means that there's already 51 cards left in the deck now, because I already took the 2 of hearts out, and now instead of there being 13 hearts, there's now 12 hearts. So for that first heart, I had 13 out of 52. There were 13 out of 52 cards that were hearts. Now I want to get a heart a second time. Well, the problem is now there's 12 hearts left because I already pulled one out, and there's 51 total cards left. So now the probability the second time I go into that deck of cards changed. So these are not independent events. Okay, because the outcome of one did change or affect the outcome of the next event. So the only way to prevent this would be if I take this 2 of hearts and put it back into the deck. That way when I reach in a second time, I still have a 13 out of 52 chance to get a heart. But we all know when you're dealing cards and playing card games, you don't put the cards back, you keep them. So that's why we have a lot of non-independent events there as well. So just remember that independence events are 2 events where the outcome of one will not affect the outcome of another. All right, so I want to talk about kind of notation with probability real quick as well. So remember we use this idea of P for probability, and then inside the parentheses we put the event that we're talking about, okay, the event that we want. So if I said, what's the probability that you reach into a deck of cards and you get a diamond? make a little diamond shape there. Well, you're going to think, okay, so how many cards are diamonds? Well, there's 13 cards that are diamonds, and there's out of 52 total cards, so 13 out of 52 cards are diamonds. That's just kind of this notation of this P there with the probability. All right, so we're going to use that throughout, and I'll keep explaining that as well. Now, there are a couple probability rules that we need to be familiar with, and the first one is what we call OR probability. Now, this is really important because I want you guys to understand what the definition of OR means here, okay? Because sometimes kids can get a little bit lost, a little bit confused with what OR means, okay? Now, remember, if I have two events, okay, I have event A, and then I have event B, all right? So I have event A, and I have event B. Now, if I say, what's the probability that event A or event B happens, you have to understand what that means. Now, OR would mean A or B or both. So the word OR means one of the events or both of the events. Now, a lot of times, some students forget about the both. So please remember that OR means one of the events or both of the events. So the event A or B consists of all experimental outcomes that are at least one of the two events. Okay? Now, we use a particular symbol for this. So we would say the probability of A or B. So we use this upside down U symbol to represent OR. I know it's kind of weird, but it's like an not upside down, it's a U looking symbol to represent OR. So A or B, this little A or B represents A or B or even both. Okay, and if it was three events, A or B or C, then it would be A or B or C or all three. So you have to understand that A or B means one of the events or both of the events. Okay. Now we're going to talk about some problems involving OR. So the definition for this is quite simple. So it'd be the probability of A or B. If you're trying to find this probability, you simply take the probability of A and you add to it the probability of B. Makes sense, right? Probability of A or B. Well, it's probability of A plus probability of B. But there's a slight issue here. Now, the issue is if these two events are disjoint, meaning if A and B cannot happen at the same time, then you're done. This is certainly the rule, and it's a very easy rule. However, if they're not disjoint, if there is some overlap, which means that they could happen at the same time, which means there is some both, right? Both means that they happen at the same time. You don't want to count them twice. So you need to subtract away the probability of A and B. Now, and means both, right? A and B. So A and B, it's both, right? So the idea of finding the probability of A or B is you take the probability of A plus the probability of B minus the probability of A and B. And the reason for the minus here is if there is any overlap, it's going to be counted here as A or it's going to be counted here as B. Okay? And I don't want to count any of that overlap twice. I need that overlap to count. I just don't want it to necessarily count twice. We're going to look at some examples shortly here that will explain that a little bit further. Now we also have AND probability. The probability of AND means, so if I have event A here and then I have event B here, AND means both events must occur. Not one, not the other, both events, right? So AND means both. Okay, now the symbol we use for AND is an upside down U. So we'd say the probability of A and B. Now the answer to finding this is a little bit tricky. We got to learn a little bit more as we go on here. We're going to come back to this, but the events A and B consist of all experimental outcomes that are both the event A and the event B. Okay, so we have to think of all of them that are both of them, both. So that's why when we come down here and we talk about OR, we actually have to kind of consider both because right A here, A and B, remember this AND means right there, that upside down U. So when we're trying to find the probability of OR, A or B, we actually need to think about the AND. Is there any overlap? Could these two events happen at the same time? Okay. Now lastly, we have what's called conditional probability. Conditional probability is the probability of something happen given that something else has already occurred. So this kind of relates to independence in a way, because if one event has already occurred and it changes the probability of the next event happening, well then that obviously is not independent, and then we have to deal with this, what we call conditional probability. So conditional probability means Let's kind of write down generally what it means here. It means one event has occurred, and its occurrence affects the next event. Okay. Now we have a symbol we use for this, and we say the probability of A given B. So we use this little line right here to kind of represent a given. And this means that B has occurred. So B has occurred. So the number or the event in the back is the one that has already occurred. So we're trying to find the probability of A given that B has occurred. So if B has occurred and affected A, then we have, well, not independence, right? Because B has affected A. Now we actually have a formula for this, but we kind of, this concept of conditional probability actually really teaches us a lot. Now the formula for this is simply the probability of A and B, remember that symbol there means and, divided by the probability of B, the condition alone. So we have find the probability of A given the B has already occurred. This is equal to the probability of A and B divided by the probability of B. And we're going to look at several examples of this as well. But I also want to talk about something else really important here for a second. Okay? Now remember, if the probability of A given B, now think about this for a second. This means B has occurred, and I want to determine what happens to A. Now, if this equals the probability of A, I have independence. And this actually might finally, maybe, put some sense to independence. And what this means is that if the probability of A is the same as the probability of A given B, then it shows that B didn't matter, or B did not influence A at all. Meaning if the probability of A, without even considering B, so over on this side I don't even consider B, B's not even an issue, it's just, hey, what's the probability of A? If that is the same as the probability of A when given B, if those two things are the same, when those two things are equal, then you actually have independence confirmed. And that's really, really important, right? Because we've been kind of talking about independence for a while, and it's really important for us to confirm when independence actually does happen. All right, so let's look at a couple examples here. Okay, first off, suppose a jar is filled with M&Ms. It contains 14 red, 10 blue, and 6 green. Let me ask you some simple questions. The first one I could say is, hey, what's the probability you reach in and you get a red M&M? Okay, well, reach in, there are 14 M&Ms that are favorable to me out of, let's see here, that's 30 total M&Ms. So that is my answer, 14 out of 30. Now, that is a proportion. Obviously, I could find that out to be about approximately 46.67%, whatever. I can get a percentage, I can get a fraction. I can even reduce that if I want. That reduces to 7 over 15 for a nice reduced fraction there, but you get the idea. Okay, now what if I said, what's the probability you get a red M&M, let's see here, or a blue M&M? Okay, so let's see, red or blue. This is simple. Well, I want a red one, so we learned a little bit earlier our formula for or says, okay, well, the probability of a red one is 14 out of 30. That's nice. Or the probability of blue one will make us happy too, so we have 10 out of 30. Now, I always have to consider, is there any overlap? Is there anything that I need to subtract away? Could these two things happen at the same time? Could I get an M&M that is both red and blue at the same time? Of course, that answer is no, so that's a big zero. They cannot occur at the same time. There is no M&M that is both red and blue. So that obviously cannot happen, so I don't have to worry about subtracting anything away. So my answer would be 24 out of 30, which I could, of course, reduce and so forth. But you get the idea. You always have to consider when you're doing or, could they happen at the same time? Is there any overlap? Because that would need to be subtracted away. Okay, now I could also do a problem like this. Now I could start talking about more trials here, right? Okay, so let's talk about 2 trials. I'm going to reach in and pull out 2 M&Ms. So I want to find the probability I reach in and get 2 red M&Ms. Okay, now This is really where I have to think, and this is where we kind of we understand conditional probability, right? So the first time I reach in, I want to get a red M&M. That's 14 out of 30. Now, I'm going to reach in a second time. Now, the key thing here is, what did I do with that first red M&M? If I ate it, so non-replacement, right? I ate that M&M, or I threw it away, or I gave it to a friend. I did not put that M&M back. The next time I go back in, there's 13 reds and 29 total M&Ms. So I would multiply to find my event, because this is two events now. This isn't just one event. This is two events. This is a red and then another red. So I would actually have to go ahead and multiply this out. So that'd be 14 out of 30 times 13 out of 29, and I would get about 20.9%. Okay, of the time I could happily. Now that's really important to understand that non-replacement thing. With replacement, things would be a little bit different, right? With replacement, and I want to find the probability of getting two reds. Well, that's going to be 14 the first time, and then if I take that red M&M, note that it's red, and put it back, well, then I got 14 out of 30 the second time as well. So this time, my answer is going to be a little bit different. My answer is going to be about 21.8%. So notice a slight difference there if you replace that M&M. So that's kind of thinking about independence without really thinking about it, or conditional probability, right? What's the probability of getting a red one on the condition of getting a red one already, or the first time? So if we want to kind of use our formula for that here, that formula I showed you a little bit earlier, I could switch colors here to show you. If I said, what's the probability of getting a red M&M given I got a red one already? Okay, well, on top, you know, it kind of gets a little confusing, as I guess what I'm trying to show you this is that you're trying to think of, all right, what's the probability I get a red and a red, a red and a red? How many M&Ms are red and red? You know, so that's why it gets a little sketchy using that conditional formula. That conditional formula is a great formula, but my whole point of showing you this right here is that this is common sense. Just think, okay, I need a red one and then another red one. Oh, but I didn't replace it. I ate it, so now there's 13 out of 29. So I just want you to think when you do those types of problems, I guess is my point. All right, next example. Two companies produce some batteries, and some batteries may be defective. So let's say we have 25 total batteries, and 15 came from company 1, 10 came from company 2. And here's the breakdown of some that were 18 were non-defective and 7 were defective. So I could ask a nice simple question. I could say, what's the probability that we have a battery from company 1? This is a real nice, easy question. What's the probability we have a battery from company 1? Well, there are 15 batteries that came from company 1 out of 25. So there's my answer. Could make a percentage if I want to. Could reduce the fraction. Easy, easy, easy. Simple, simple, simple. I could also say, what's the probability that we had a battery that came from company 1 or it was defective? So I'm asking for what's the probability that a battery was from company 1 or it was defective. Okay, well, this is an or. Or means add, right? Really simple. Or means add. Nice and simple. So company 1, 15 out of 25 batteries. Or defective. Oh, okay, so 7 out of 25 batteries were defective. So any one of these 15 company 1 batteries are going to make me happy, or any one of these 7 defective batteries are going to make me happy. The problem is that these two events are disjoint, or they're not disjoint. I mean, there are some overlap. There are some batteries that are both defective and came from company 2. So that would be these two batteries right here. These two batteries right here. Whoa, gosh, I'm sorry. Take that back. These 5 batteries right here are from company 1 and are defective. So those 5 batteries got counted in these 15 that were from company 1, and those 5 batteries got counted in these 7 that were defective. So they got counted, and I want them to count. I just don't want them to count twice. So those 5 out of 25 batteries need to be subtracted away. So I got 15 plus 7 minus 5 is 17 out of 25 is the chance of having a battery from company 1 or be defective. Okay, so hopefully that makes sense. Now let me find for you the probability that a battery is from company 1 and defective. Now, once again, don't overthink this. This is just so simple. What's the probability that a battery is from company 1 and it's defective? Well, how many batteries are both company 1 and defective? Well, that's simple. 5 batteries are both company 1 and defective out of 25 total batteries. So very, very simple. Now let's ask you a conditional probability here. So let's change it up here and do a conditional one, because those are kind of cool. So let's just say that I found a defective battery. I tested it and I 100% know it's defective. I want to find the probability it's from company 1. So I'm trying to find the probability that my battery is from company 1, but it's given, or it's known, I know that it is defective. Okay? Defective. Okay, well, let's see here. The probability is from company 1 on the condition, or given, that's what this line means right here, this big line right in the middle, that it's defective. So let's see here. The easy way to think about this is just common sense. I have to have a defective battery. How many batteries are defective? Well, 7 batteries are defective. How many of them are from company 1? 5. There's your answer, 5 out of 7. I thought through it. I said, wait a minute, there's a condition here that the battery had to be defective. That limits me to only 7 batteries I could be looking at, 5 of which are from company 1. But I want to show you how you can use the formula to get that answer too. But most kids just get that answer just by common sense. But the formula does work. Now remember, the formula is company 1 and defective on top. So how many batteries are from company 1 and defective? Well, it's 5 out of 25. We already answered that. On the bottom is the probability of a battery being defective. Okay, well, the probability of a battery being defective is 7 defective batteries out of 25. Now, you guys hopefully should all know that when you divide by a fraction, you multiply by the reciprocal, and the 25s cancel, and I get 5 out of 7. So that's a nice, easy way to do conditional probabilities. Just kind of think through it. Okay, I know the battery is defective, which limits me to this defective column here, 5 of which are from company 1, so 5 out of 7. So that should be a nice answer there. Now, another key question is the company that a battery comes from and its defective rate independent? Well, I tell you right now, no, it's not. Look back at the very beginning. We found out that right here that this was 3/5, right, or 3/5 is 0.6, 60% chance. We found out that a 60% chance of a battery coming from company 1. But then down here we found out that if that battery is defective, there is now a 71% chance that it's from company 1. So this defectiveness made the battery being from company 1 increase. So think about that. That means not independent. That means that being a defective battery changed the probability of being from company 1. So that shows that company 1 and defective batteries are certainly not independent. Okay? All right, last major example here. Rolling a die. Rolling 2 die is a popular example. So I wanted to show you a sample space here. These are all the 36 options. Why are there 36 options? Because there's 6 options for the first die times 6 options for the second die. So 36 total options. Now, one thing that we often do when we roll 2 die is we add up the sum of the die. So if I wanted you to list a sample space, what are the possible sums, right? What are the possible sums when you roll a die? Well, could you ever get a 1? Nope, it's impossible. The lowest you could ever get is a 2. And you could get a 2 and a 1, or a 1 and a 2. That would make 3. So you could also have a sum of 3. You could have a 2 and a 2, or a 3 and a 1, or a 1 and 3. That's a sum of 4. You could have a, let's see here, a 2 and a 3. That's a 5. A 2 and a 3, it's a 5. A 4 and a 1, or a 1 and a 4. So you could have a 5. And I just don't want to bore you to death here. You could have a 6. You could have a 7. You could have an 8. You could have a 9, you could have a 10, you could have 11, and lastly, you could have a sum of 12 if you roll that one rare 6/6. But obviously, the sum will never be bigger than 12. So I'm talking about the sum. There's my sample space. So let me ask you a couple questions here, and I'm going to have to move around here a little bit so we can get it all covered. All right, so first off, I could ask something real simple like, what's the probability that you get an even sum? What's the probability you get an even sum? Well, that would be, let's see here, a 2 would be even, a 4, a 6, an 8, a 10, or a 12. So all those that would make me happy. So I got to think of all the different ways that can happen. So how many different ways can I roll a 2, for example? Well, there's only one way to roll a 2, a 1 and a 1. How many ways can I roll a 4? Well, 2, 2, a 1, 3, 3, 1. There's 3 ways to roll a 4. And you could actually see them up here. If you come up and look at the chart here, you could see the 3 ways to roll a 4. How do I roll a 6? Well, that could be a 3, 3, 4, 2, 2, 4, 5, 1, 1, 5. So there's 5 ways to roll a 6. 1, 2, 3, 4, 5. How many ways to roll an 8? Well, you get a 4, 4, 5, 3, 3, 5, 2, 6, or 6, 2. So there's 1, 2, 3, 4, 5 ways to roll an 8 as well. How about to roll a 10? You could roll a 6, 4, 4, 6, or 5, 5. So there's 3 ways to roll a 10. And once again, there's only one way to roll 12. So add those up. That's 5 and 5 is 10. 3 and 3 is 6. That's 16, 17, 18. So there's 18 out of 36 ways to get a sum that's even, and that ends up being 50%. And that should make sense. 50% of the sum should be even, 50% should be odd. Makes a lot of sense. Now, let's ask you a conditional probability, right? Let's say, what's the probability that you roll a sum of, let's see, a sum of 7 given that the sum is even? Okay? What's the probability you roll a sum of 7 given that the sum is even? Okay, well, let's think on top here. On top goes 7 and even. How many different ways can I roll a 7 and have the outcome be even? Now, just think about that for a second. How many different ways can I roll a sum of 7 and have the outcome be even? It's impossible. Never. Can't happen. 0 out of 36 ways, or you could have a sum of 7 with it being even. It's impossible, right? Because it can't happen. If you roll a 7, then your sum is already odd. On the bottom would go the probability of being an even, which we just figured out was 18 out of 36. Divide those, the 36 is canceled, but you still get 0. There's a 0% chance that can happen. Hopefully that makes a lot of sense. Very, very simple. Okay, I could say, what's the probability we get, let's see here, a odd or a sum of 6? Okay, what's probably giving an odd or a sum of 6? Well, odd would be 18 out of 36 odds, or plus rolling a 6 would be, well, we already did that one already. There's 5 out of 36 outcomes. Don't forget about our overlap, though. Are there any overlap here? Can I have any outcomes that are both odd and 6? Now, that's impossible because 6 is even, so I can't have that happen. So I'd have to get rid of 0 out of 36, and I didn't worry about it. So it'd be 18 plus 5 would be 23 out of 36. So hopefully that makes sense. Hopefully that was pretty easy. And for the most part, hopefully the beginnings here of probability makes sense. And hopefully you don't have any major questions.